Saxon Algebra 2, Lesson 17. I'm sorry, you guys. I could not even write 17 without it looking like some sort of, I don't know, Japanese house calligraphy. So that's kind of crazy. But I promise I'll do better on my numbers in the rest of the lesson. Okay, two topics today. First one, algebra. Second one, geometry. Both are fun and both are to the point. Subscripted variables is where we're starting. Remember, subscripted variables are just a little stylistic flourish that we can use to help us match our words in a story problem to the equations that we're creating. It just helps us connect the dots between the words and the numbers. So, right now, we're not going to talk so much about the words. We're just going to be given the equations with the subscripted variables in them. And then later we'll add in the words and you'll see, oh yeah, this does actually make a ridiculous amount of sense. And this is all review. We did this last year. Okay, so when I write an equation like this, you are experienced enough mathematicians to know, oh, I remember these problems. This is this whole number of nickel, number of dime things. Right? And this is a system of equations. We want to solve it together. And we remember, oh yeah, these are these coin problems, right? And there was something about the number of coins and then what the coins, their value was, right? Because 5 cents is a nickel and 10 cents is a dime. We'll get to all that story stuff later. Right now, we're just going to practice, we're going to practice solving these equations. We've already been practicing substitution and elimination. Now we're just practicing it with this little stylistic dealio here with the number of nickels, number of dimes. It doesn't change anything, you guys. It's not really that big of a deal in terms of context, but it just looks kind of weird. All right, so we decide to solve this by elimination, and we decide, John decided for us, but I'm not going to argue with him. He would like to multiply this one by -5 so that this line will cancel. Or the ends will cancel. So this is our A, this is our B, this is -5 times A. And that will be, so I'm distributing this. This is -5 times the number of nickels minus 5 times the number of dimes equals 5 times 40 minus 200. Make sense? Now I'm going to combine -5A plus B. So I'm smushing these two lines together. This part cancels. Oh, I love when that happens. 10 minus 5 means I have 5 and D, and then that subtracts and I get 50. Oh, John, I love when it comes out even. So the number of dimes equals 10. And then I can go right here to my original equation and see that the number of nickels must be 30. And then together they add up to 40. So that's the way I double check that. When I was in college, I studied accounting and I worked in the super cool, and I'm actually not being sarcastic, I loved public accounting. It was a really fun, interesting job, despite all the stereotypes. And when you get to a final answer and you've checked your work, you put a double underline. So this is our answer. Yay. Okay, so the subscripted variables don't change a single thing. They just look cool. Next one is a different style of problem. Again, we did these last year. These were the ones where we had the base equations. Right? It's got all these variables in it. And then we had some smaller equations that went with it. This is an M. This is a W. Got a little crazy there, didn't it? John writes all of these in a row. I can't fit them in, but we can see that this big long one, that has all the variables in it. That's going to serve as our base equation. Then this one, we can just substitute the number in there. This one, we can substitute the number in there. And then this one, we have to rearrange it so that we can substitute either for TM or TW. Remember, it's rates and times, or the R and the T. But we don't need to worry about the story. I'm just going to subtract this second one. So I'll say TM equals 5 minus TW. Okay, we could have subtracted the TM. That would work just as well. I just decided to keep the first one and move the second one. That's all. All right, so now all of these are ready to substitute in. So I'm going to rewrite this equation with buckets for all 4 of these, even though I don't have all 4, but that's okay. It'll work out. 260. So RM is 40. That goes in here. RW is 60. That goes there. TM, that's this one, is 5 minus TW. And then I don't have anything left to put into this one, so I just put the TW in. And I get all excited because I go, oh, look, those match. So it's going to work out. Because in order to actually solve an equation, you have to have just the one variable, right? So that's good news. All right, so now I need to distribute here. And then we'll add, and then this I'll just multiply. I don't need the parentheses on there. And we'll be in good shape. So 40 times 5 is 200. Minus 40 TW. Okay, plus 60 TW. Equals 260. So, what should we do next? I wish you were here so I could ask you all these questions myself. We're going to combine like terms here, and then we'll swim the 200 away. This cancels. These two together give me 20 TW. And when I add those two, I get 60. Divide, and I get TW equals 3. And what does John tell us to do? Solve the following system of equations. Okay, that means that we have to have, everything has a value. We've already got this and this, right? They've got value. So we just need TM and TW. We just got TW is 3, and we can see right here, oh, TM equals 5 minus 3. So TM must equal 2. Oh, and here it is again. Also, right, the 2 T's have to add up to 5. So, looks like we nailed that. TM is 2, TW is 3. Yay! Okay, so 2 different types of systems of equations. Both are review from last year. Both are straightforward. The subscripted variables don't change a thing. Moving on. Now for the geometry part of this lesson. Are you ready? Angle relationships is what it's called. I don't even know what that means. Angle relationships. But what we're going to do is we're going to take a look at a geometric diagram and say, okay, what do we know about how the numbers should behave given the picture? We have here 2 parallel lines, all right? And then we have a line that chops through like that. And then we have some numbers and symbols. And we have to make sense of that, and we're supposed to find X and Y. All right, well, what are we looking at here? Well, let's see, the parallel lines and the line chopping through it, that's a transversal. Right? That's what we call that. We studied that way back in the beginning of the year. We reviewed that. And we know that when this kind of thing happens, we get a pattern of angles, right? Larger, smaller, smaller, larger. Oh, this is too close. And then smaller, larger. No, sorry. Right? They keep repeating that pattern over and over. So that means that we can use this information to say some things. Okay, so this is a straight angle. This much is 50, so I know that this much must be equal to what, 130, right? Because it has to add up to 180 in total because it's a straight line. Conversely, okay, if this side is 50 and this is 130, then once I get down here, this is the 130. And so now this side has to equal 50. Does that make sense? I just follow this pattern and bring my numbers down. And I know that whatever this crazy expression is, it has to be equal to 50 because that's the pattern that the angles make. So now what I can do is I can use these two equations to set up a system and solve for x and y. So my two equations are that 7x minus 2y equals 130 and 5x minus 10y equals 50. Just a reminder that this presentation with the parentheses, those are on there because John wanted to tell us that this whole expression represents the size of the angle. So he put parentheses around it and then put the degrees on the outside. So it's just a way of making it clear to us that this whole thing represents the size of that angle. And that's good because then we can say, well, that whole thing must be equal to 50. All right, so here's our system of equations, and now we just solve it. Okay, so the hard part is setting it up. And the hardest part of all was just remembering when we saw this picture, oh yeah, there's this pattern, and using the 50-degree angle, we can figure out how big both of these angles are, and then we can chase it down here and know, oh yeah, this must have the same pattern. Now we are ready, and then we wrote those equations, and here we go. All right, what should we do to fix this? Well, I think I don't like the x's because 5 and 7 are both going to need adjusting. This one I like better. Let's do a and b. Because if I multiply a by -5, that'll make that positive 10y and then everything will cancel. All right, so that's what I'm gonna do. I'm gonna write -5a, and I did that, remember the way we determine what we wanna do is by looking down the columns and looking to see which is easier to create the same number, only positive and negative opposites. All right, let's multiply line A by -5. It'll be -35x plus 10y equals, well, what's that? -650. Huh, that's kind of intense, isn't it? And then we will add -5a plus b. Okay, so I'm just going to squiggle this out so I don't get confused. But now I want to add these two. -30x, goodbye, equals -600. Oh, divide by -30, and we get x equals 20. Okay, perfect. Now, 20 is not the size of that angle. 20 is the value for x. 20 is an algebraic answer. It's not a geometric answer, okay? It doesn't describe any angles. It's just an algebra problem that we made up from the angles. It's important that you understand the difference. If John asked you for the size of this angle, we would have to, well, we still have to solve for y, but we would have to plug it in and then create a number there to get the angle size. This is just an algebraic number. But it's cool because now we can take this and plug it into one of our original equations to solve. I vote, no, let's just put it in the first one. 7 times 20 minus 2y equals 130, right? So I'm using the original one we set up. And this is 140. So I subtract 140 from both sides. I multiplied 7 times 20, in case I went too fast. Minus 2y equals -10. And we get y equals 5. And that's the correct answer. Beautiful. So this is an example of the kind of geometry that I personally like, that I think is more fun, is where we take a geometric idea and we tease some algebra equations out of it and then solve those. And again, y does not represent any value of an angle. Y represents an algebra value that John made up to describe those angles. Okay, I'm done here. Lesson 17 is history. I will see you for lesson 18. I guess you're probably watching these together back to back, so I'll see you in a minute. Bye.